Alrighty, good morning everyone, and welcome to the wolfSSL live webinar, getting started in 2021 with wolfSSL engineer Chris Conlon. My name is Kajal Subkota, and I will be moderating this webinar. All attendees will be in listen-only mode, and if you have any questions, please feel free to use the Q&A box or raise your hand to be unmuted if you would like to ask the question live, as we do host a Q&A session following the presentation. This webinar will also be recorded and made available via our YouTube channel shortly after the presentation. I invite everyone to follow us on Twitter at wolfSSL, as well as all of our other social media. Please feel free to email us at facts@wolfSSL.com if you have any additional questions. And now I'd like to give a brief company overview before we move on to the technical presentation. wolfSSL was founded in 2004 by Todd Auska and Larry Stefanik when they realized there wasn't an open source dual licensed embedded SSL library available. OpenSSL existed at the time, but there was a demand for an alternative that was easily portable, smaller, faster, available under a clear commercial license, was equipped with a clean and modern API, and offered commercial-style developer support. wolfSSL was born into this market need with an open SSL compatibility layer. Today, wolfSSL secures over 2 billion connections. We have more than 1,000 OEM customers and dozens of resellers. wolfSSL is made up of almost 40 dedicated employees in 2020, most of which are engineers. This process is, of course, supported by a strong partner network that we're very proud of, which includes Microsoft, STMicro, and Curl, for example. Since the beginning, our engineering team has developed several embedded security products, including wolfCrypt with DO178 support, FIPS certification, and a FIPS ready offering, MQTT up to the version 5 specification, SSH version 2, TPM 2.0, a secure bootloader known as wolfboot, as well as Java wrappers and JSSE support, and commercial support for curl. All of these offerings are accompanied by thorough maintenance and support plans up to the 24/7 level. We also offer full service consulting. And now I'm going to hand things over to Chris.
Great, thanks Kajal. And hey everyone, my name is Chris Conlon. Thanks again, like Kajal mentioned, for joining us today. We have a great webinar planned for you today on how to get started efficiently and effectively with wolfSSL. We're going to start out with a quick overview of SSL and TLS and some of the differentiators of TLS 1.3. We'll go into wolfSSL next, our SSL and TLS library, giving you an overview of the library, going through the package structure of what you'll see when you download wolfSSL, how you can build wolfSSL. I'll talk about our wolfCrypt test and benchmark applications and how you can use those to easily get started and see benchmarking results on your platform. I'll go through some basic library usage and end in some helpful debugging tips that you can use if you run into problems along the way. I'm planning on doing a quick live demo of our benchmark application at the end of that, and we'll end in a question and answer session to give you a chance to ask any questions you might have. So we'll start out with a quick overview of SSL and TLS. It was founded in 1995 by Netscape. The first protocol released to the public was SSL 2.0. In 96, SSL 3.0 was released. And in 1999, the protocol changed enough that it warranted a name change to TLS, or Transport Layer Security. So SSL itself is now insecure, both 2.0 and 3.0. TLS is what people are using today. TLS has gone through 4 revisions, 1.0, 1.1, 1.2, and the newest version being 1.3. And then paralleling TLS development has been DTLS, which stands for Datagram TLS. This is a version of TLS designed to be run over unreliable protocols such as UDP. So if you're using a VoIP application, that might be a good example of a DTLS user. TLS sits in between the transport and application layers. Here's a simplified diagram of the OSI model, where you have your network internet transport layers on the bottom. SSL, TLS subprotocols are shown in blue here. And then green boxes are just examples of application protocols that could be either running on top of TCP/IP or your transport layer, or on top of SSL for a secure communication. And SSL and TLS does provide three things: authentication, confidentiality, and integrity. So when a client and server first start communicating over SSL TLS, they do what's called the TLS handshake. Here's a kind of a simplified version of that handshake in diagram form. So there's several round trips that go back and forth between the client and server with the goal of establishing the secure communication channel. They exchange certificates, authenticate both sides of the parties, and agree on a common cipher suite and set of algorithms that'll be used. TLS uses what's called a cipher suite, which is essentially a string representation of the algorithms that will be used in that TLS session. So here's kind of what a string would look like in TLS 1.2 and before. So you start with the TLS protocol, key exchange algorithm, the bulk encryption algorithm in an optional mode, and followed lastly by the message authentication function. And here's some examples of what you might see as a TLS cipher suite string in TLS 1.2. If you've configured a web server or used TLS before, these probably look fairly familiar. Or if you've clicked on the green lock in your web browser and explored what cipher suite your web browser is using, that's another area you might have seen something like this. So in our industry, one of the more exciting developments that's happened in the last couple of years is the development and release of TLS 1.3. So this is the most current TLS protocol. It was in development for 5 years with 28 drafts between when work started in August 2013 and when the RFC was officially recorded in August of 2018. It was given the RFC number of 8446. And if we look at some of the highlights of what changed in TLS 1.3, there were algorithm changes, removal of some insecure features. Most of the handshake messages are different, and there's more of those messages that are encrypted. There's a new zero RTT or zero round trip time mode where application data can be sent in the first flight. Redesigned key derivation functions, and also changes to how session resumption is done. So advantages to you as a user. The first of these is it's going to be faster in performance. TLS 1.2 and before took 2 complete round trips to establish a secure connection. TLS 1.3 only requires 1 complete round trip. So this saves transferring data over network. It also means that network latency has less of an impact on the time required to establish that secure connection. And then optionally, there's the new zero RTT mode, where if you need application data to be sent and received by your server quicker, you can send that with the first client hello message. The second big advantage is it's more secure. So the protocol designers removed a lot of the legacy and insecure algorithms. Some of those are listed here on this slide, include RSA key transport, since it lacked perfect forward secrecy, RC4 stream cipher, CBC mode ciphers, SHA-1 hash functions, arbitrary Diffie-Hellman groups, and also export ciphers. So it makes it harder for users to incorrectly use TLS and be using one of these things that would be insecure from the beginning. And it also can be more flexible for some use cases of TLS. So with TLS 1.3, there's a new mechanism that allows a key update without reestablishing the entire TLS session before you needed to close down the session and reopen it. It allows post-handshake authentication. So in TLS 1.2 and before, authentication of the client and or server needed to happen during the handshake. Now you can do that anytime after the handshake if you need or would like to. And then kind of a side effect of removing some of those insecure features is that it can help reduce the library footprint size. So if you'd like to learn more about TLS 1.3, go ahead and head over to wolfSSL.com/TLS13. And we've got a bunch of good resources for you there, and we walk you through how you can use that in wolfSSL inside of your application. So now let's move on to wolfSSL. This is our SSL and TLS library, and kind of the topic of today's webinar with getting started with wolfSSL. So wolfSSL is our SSL and TLS library. It's very lightweight, portable. It's all written in C with some assembly for certain platforms. It supports up to TLS 1.3 and DTLS 1.2. Footprint size ranges from 20 to 100 kilobytes, depending on how you have the library configured and your compiler that's being used. Runtime memory usage is 1 to 36 kilobytes per session. Footprint size, if you're comparing this to kind of our closest open source competitor, OpenSSL, is 20 times smaller. So it's going to fit much more easily in embedded IoT type environments. And we've ported wolfSSL to almost every OS and RTOS that we've encountered today. You can see the list on the bottom of this slide. Everything from your standard Windows, Linux, Mac, through a bunch of different RTOSes, all the way down to just a bare metal environment. Some additional features, we have an OpenSSL compatibility layer. This is probably at least 1,000 of the most commonly used OpenSSL functions that we map internally down to wolfSSL. So it can make it very easy to migrate from using OpenSSL in a project over to wolfSSL. Oftentimes it's as simple as just switching your linking to wolfSSL. We've integrated into a number of different web servers, including Apache, Nginx, Lydie, and Mongoose. And one of the other big differentiators for wolfSSL is our support for hardware-based cryptography. So if you have crypto in your silicon available, oftentimes if we have the support for that already, we can offload and call that crypto instead of our software crypto, giving you performance increases and code size reductions. wolfSSL is NSA Suite B compatible and also have our FIPS 140-2 validation. We are working on 140-3, which will be coming sometime soon. Underneath wolfSSL sits wolfCrypt. This is our cryptography library. wolfSSL uses it for all the crypto operations, but you as a user can also use it directly. It's set up to be very modular in manner, meaning you can compile in and out almost all the algorithms on a per preprocessor basis. And this is just a list of the algorithms we currently support, which is all of your standard algorithms, including some more progressive ones like CHA-20, Poly 1305, and Curve and Ed 25519. So the first step to kind of getting started is to download wolfSSL. So you can do that from either our wolfSSL website, where you'll get our stable releases, or if you prefer to track us on GitHub, you can download us from github.com/wolfSSL. So once you've downloaded the library, next up, we're going to take a look at what you see there as the wolfSSL package. Oftentimes, now we've got a lot of different files in there. It can be a little overwhelming to know what's what from the get-go. So once you download the package and look at it, you're going to see something that looks like this. And the next couple slides, I'm just going to walk you through some of the key areas of where you might want to look, depending on what your goal is. So starting at the top and working our way down, the IDE directory, this contains compiler project files for a bunch of different compilers and development environments. So if you're looking to open wolfSSL up as a project in your favorite development environment and hit compile, this is the place you'll want to look. The certs directory contains example certificates and keys. So we use these in our own testing and also ship them for you to, kind of get up and running quickly. It's not meant for you to use these in production, but definitely in prototyping and testing, they can come in very handy. wolfSSL uses the autoconf and configure system by default when running on a Unix, Linux type platform. So you'll find a configure script here in the root, which can be used to configure the library. The CYASL and ctowcrypt directories, this is a backwards compatibility layer, I should say, for CYASL. So but we changed our name several years back of the product from CYASL to wolfSSL. And these directories just contain the kind of a compatibility layer for the old API. The examples directory, this contains examples for a client, server, echo client, and echo server. This can be a good place to look for API usage examples. Also, these are helpful for testing. Depending on if you're a client or server, you can test against a known working example on the other side. gencertbuff.pl, this is a Perl script that we use to generate C arrays from a certificate or key file. Oftentimes, embedded devices that we work with or our customers are working with don't have file systems available. And so this is just an easy way to take a file and get a C array version of that. Now we'll skip down towards the bottom, the wolfCrypt directory. This is the source files for our crypto layer, wolfCrypt. The wolfSSL directory is our header file location. So wolfSSL includes the SSL and TLS headers. wolfSSL/wolfCrypt contains our crypto layer headers. And wolfSSL/OpenSSL is our OpenSSL compatibility layer. And then near the bottom, we have a bunch of Visual Studio solution files for those of you on Windows. And then the last directory that you'll see there is a wrapper directory. This contains our C# wrapper. We do have other language wrappers for Java, Python, JavaScript. Since those are a little bit larger in size, we've chosen to package those separately. So the only one located in the wolfSSL package itself is the C# wrapper. Okay, so now that we've gone over the package structure, let's look at how you would build wolfSSL. So on Linux Unix, wolfSSL uses autoconf to configure and make the library. If you've used other Unix type packages before, this is probably very familiar for you. If not, it's pretty straightforward. You run configure with your set of options to enable or disable, run make to compile the library, and make install to install that library. Configure does have a help argument that will dump out all of the available enable options for you to use. We do have quite a few now. We probably have in the order of several hundred. So either you can look to that, or our support team can help guide you to find the right options for your goals. Once you've identified what enable options you want to use, you can append those to configure. So for example, here we're enabling ECC and DTLS, and then running make to compile the library. You can pass preprocessor defines through configure by using the cflags variable. And you can also run make check. This will compile the library and also run our built-in tests that we have plugged in. And then doing a make install or a sudo make install will install the library. By default, this is installed to user local, where the headers go into user local include wolfSSL, and the library gets installed to user local lib. The wolfSSL artifact itself is called libwolfSSL. Extension varies depending on if you're building a shared library with .so or .dylib, or a static library with .a. So for those of you compiling on Windows, we have those Visual Studio solution files that I pointed out. We have solution projects for the example client and server, echo client and echo server, our SSL sniffer, our test suite, and for the main wolfSSL library. And we've got some more detailed instructions for Visual Studio build available on our website. We also have Windows users who choose to use Cygwin to compile. With that, helpful packages here for Cygwin are going to be automake, autoconf, libtool, make, and unzip. And then after you have those installed and set up, simply just follow the autoconf instructions for Unix and Linux type environments. And then there is an install file located in the root of the wolfSSL package. This includes some instructions for pointing you in the right direction on compiling for some specific platforms. So for example, if you're looking to compile for, with IAR or a Microchip or Freescale NXP platform, it would be helpful to take a look at the instructions located here. Now, the other type of compiling scenario we run into is when a user wants to just directly build the SSL and TLS and crypto library into an existing IDE-based project. And so doing this is pretty simple. You just need to know where to look. You'll want to pull in the right source files for the SSL and TLS layer, which is located under the ./src directory. And for the crypto layer under wolfCrypt/source. And then the header files you want to pull in are the wolfSSL ones under wolfSSL and the crypto level ones under wolfSSL/wolfCrypt. Portability has been in mind, ever since we started really developing wolfSSL. And we've tried to abstract out most of the system level and platform level dependencies. So things like IO, logging, memory handling, all that has been abstracted out and makes it easier to move to a new platform if you need to. You can find our existing port layers in the wolfSSL/wolfCrypt/settings.h file. If you look in there, we have one defined per port. So for example, there's a define called FreeRTOS for building with FreeRTOS. If you're using LWIP, there's a define called wolfSSL_LWIP. Now for customizing the build, we recommend that you define wolfSSL user settings when compiling wolfSSL. And what this will do is cause wolfSSL to include a header file called user_settings.h. And you can put all of the defines and settings that you want to use to customize wolfSSL into that header file. And that gives you kind of one singular point that you would need to maintain going from release to release of wolfSSL. If you want kind of an example of looking at a user settings, a good one is in our IDE/Rally Crossworks ARM directory. There's a user settings.h in there that's populated with most of the preprocessor defines available to you that you could use in your own user settings file. Okay, so now let's move on to the wolfCrypt test and benchmark application. These are two applications that ship with wolfSSL. So the first one, this test application, is located in test.c under wolfCrypt/test. And what this does is run a bunch of cryptography test vectors through all the algorithms that are enabled by default in wolfSSL and wolfCrypt. And it verifies the cryptography level is working correctly on your platform. And so we recommend this is the first place you start when getting wolfSSL or wolfCrypt running on your platform. If the crypto doesn't work right, then everything above it isn't going to work right either. So it's better to figure out, start at the bottom and work your way up. So the wolfCrypt test application is compiled when you run a make. The executable is called test wolfCrypt and can be executed from the root directory by using wolfCrypt/test/test wolfCrypt. When you run that, it'll look something like this. You'll just see an algorithm followed by either test passed or test failed. The second application that ships with wolfSSL is a benchmark application. And so this lets you benchmark all of the enabled cryptography algorithms in wolfCrypt and ideally run this directly on your target hardware. It allows you to easily compare things. Say you're comparing software versus hardware cryptography, or if you're comparing wolfSSL to another implementation. And we also have some kind of reference benchmarks, which when we collect benchmarks with this application, we put them on this website linked on this slide. So the executable here is called benchmark. It's again compiled when doing the normal make. And you can run it from the root directory by running wolfCrypt/benchmark/benchmark. When you run the benchmark, it'll look something like this. You'll get an algorithm, the throughput of that algorithm in megabytes per second. And also if supported on your platform, you'll see cycles per byte. So if we look at the structure of test.c and benchmark.c, by default, they include a main function. By default, they use certificate and key files. They assume they're kind of running on a desktop-like system, and they do benchmark all the enabled algorithms by default. The good thing is, it's easy to customize these to be more friendly for running on an embedded system. You can reduce the resource usage of these by defining bench_embedded. You can use certificate and key buffers instead of files by defining one of the three defines listed on this slide. If you already have your own driver function, you can eliminate the main function by defining no main driver, and that exposes a wolfCrypt test or benchmark test function, which you can call from your own driver application code. You can also benchmark or test algorithms individually. Each algorithm will have its own test or benchmark function. Okay, so let's move on to basic usage of the library. So the first thing you want to do when starting to use wolfSSL in your application is make sure your application is compiled with the same preprocessor defines as the wolfSSL library. If you have a mismatch there, it can cause some very weird things to happen, some seg faults or undefined behaviors. If you're using the autoconf and configure method of compiling the library, that'll generate a wolfSSL/options.h header for you. And it puts all of the preprocessor defines that wolfSSL was compiled with in there. So all your application has to do is include that as the first wolfSSL header. The main wolfSSL header for SSL and TLS functionality is wolfSSL/ssl.h. We have two main structures in the library, a wolfSSL structure, which represents a session, and a wolfSSL CTX structure, which represents a context. The context acts as a factory for sessions. Typically, an application would have one context and then one session per TLS connection that you would like to make. You'll initialize the wolfSSL library with wolfSSL init. Optionally, you can enable debug output by calling wolfSSL debugging on. You'll create a wolfSSL context structure with wolfSSL CTX new that accepts in an argument that represents the protocol version and side of the connection that you're on. So here we're making a context with TLS 1.2 on the client side. You can enable or set how peer verification is done using the wolfSSL CTX set verify function. So here we're enabling peer verification with SSL verify peer. You can also optionally pass in a callback function as the third argument. And if verification fails, that callback function will be called. Next up, you'll want to load in your CA certificates for verifying the peer. So you can do that from a dir formatted buffer in this example using wolfSSL CTX load verify buffer. You can also load in a file using wolfSSL CTX load verify locations. Your application would then go on to create and connect the socket or other transport medium if you're not using sockets. Then you'd create a new wolfSSL session for that connection using wolfSSL new, and you'd pass the socket descriptor in the case that you're using TCP/IP using wolfSSL set FD. So after that, you're ready to do the handshake with the peer. So you can do that if you're on the client side by calling wolfSSL connect, or on the server side by calling wolfSSL accept. When this function finishes, you'll have a established TLS session that you're ready to do secure communication over. So you can write data using wolfSSL write, or read data using wolfSSL read. When you're done with that session, you'll shut it down by calling wolfSSL shutdown, and then free resources at the session level, the context level, and the library level. For API usage details, the wolfSSL API reference is located in chapter 17 of the wolfSSL manual. We also do have some Doxygen API docs on our website. And like I mentioned, the wolfSSL example client can also be used as an API usage example that's located under examples/client/client.c. Now, wolfCrypt, your application can also use just if you want to, say you use AES to do an encrypt directly. If you're using AES, you would include the wolfSSL/wolfCrypt/AES.h header. Each algorithm has its own header file and structure associated with it. So here you're going to be using the AES structure. If you're using a different algorithm, that structure name would change. And for wolfCrypt API details and reference, I would point you towards chapter 18 of the wolfSSL manual. Now, just a note about thread safety. wolfSSL is thread safe by design, so multiple threads can enter the library without creating conflicts. We try our best to avoid using global data, static data, and things that would prevent threading from multiple threads or use it from multiple threads at once. There are two exceptions, which you do need to be aware of if you're using wolfSSL in a multi-threaded environment. The first of these is that your application can share a wolfSSL object across multiple threads, but you need to synchronize access and implement some locking around that object. So for example, trying to read and write from to the same wolfSSL object from multiple threads is not supported. The second exception is that your application must completely initialize a context before creating a session from it. So that just, the reason behind that is that when you make a new session with wolfSSL new, it inherits all the settings from the context. So if that context isn't completely initialized yet, you'll have an incomplete session structure. So we recommend that you initialize the context with just one single thread to avoid any kind of synchronization issues here. So next on to just a couple notes and tips about debugging wolfSSL. So you can enable debug logging with wolfSSL by using the enable debug option with configure or defining debug_wolfSSL. And then after calling wolfSSL init, you enable debugging at runtime by calling wolfSSL_debugging_on. So that will, at runtime, dump debug log messages out. By default, those will be going to standard error, but we have ways where you can redirect those to other locations of your choosing. And what you'll see in here is logs of entering and leaving functions. It'll show you details of the handshake process, details of certificate parsing and validation, and it just gives you some more context around an error if you're trying to debug a failing connection. You also can leverage the wolfSSL example client and server for debugging. So if you're developing a client, for example, it allows you to test against kind of a known working example using the wolfSSL example server, and vice versa. So if you're able to do that, then you can focus on just developing and debugging the one side of the connection. Wireshark can be a very helpful tool when debugging TLS sessions. Our support team will oftentimes ask you for a Wireshark trace if they're trying to guide you through solving a problem. Okay, so now let's see if this works. My plan was to give you kind of a quick live demo of our benchmark application. Let's see, I'm going to switch my screen over to a terminal window. So here I have a version of wolfSSL version 4.5.0, which I downloaded from our website. All I've done so far is just unzip the directory. So here I'm going to start by running configure. And actually I can do a --help which would allow you to see, like I mentioned, to dump out of all the available enable options for you. I'll just run a basic configure for now. So it's kind of our default setup. We have things enabled and disabled, which we think are best practices. So this will go through and detect a bunch of things about your environment. It gives you a summary at the end of configure, tells you what features are enabled and disabled. Now after this, we're ready to run make to compile the library. So that compiles the library, the examples by default, some of our test applications. Now from here, this also compiled the wolfCrypt test and wolfCrypt benchmark applications. So I can run the wolfCrypt test application by running wolfCrypt/test/test wolfCrypt. You can see that here, all of these enabled algorithms passed. And then I can run the wolfCrypt benchmark application by running wolfCrypt benchmark. Here you'll see it kick off the benchmark application. It benchmarks all the enabled algorithms for at least 1 second each. It gives you throughput in megabytes per second, tells you cycles per byte. I'm on an Intel-based chip here, so we do support cycles per byte in this environment. Here you can see now we're going through HMAC benchmarks. Now we've moved into public key benchmarks with RSA, Diffie-Hellman, ECC, ECDHE, CDSA, and the benchmark is complete. So, one thing that we frequently use this for is we'd run one like this, then we would either enable or disable hardware crypto and run it again. We could see the performance numbers change to see if it's advantageous or not to enable that hardware crypto. So hopefully that was helpful for you. I'll switch it back over to our slide deck and we can open it up for any questions that you might have.
Alrighty, we have a few questions lined up here. Is CMake being supported going forward?
Yeah, so we, up until this year, we've just kind of supported CMake in some of the other IDE build configurations. This year, we put a little more effort into rounding out kind of a default CMake build for wolfSSL. So we do have that available at the moment. It's not up to quite the extensiveness of our configure autoconf support right now, but I think we'll keep working on expanding that going forward.
What happens if wolfSSL is configured with debug, but the app does not call debug in it? Post-quantum is not included in the benchmark, or is post-quantum included in the benchmark?
Sure. So yeah, two questions there.
Mm-hmm.
So if you enable debug, but don't call wolfSSL debugging on, you won't see any debug output messages being printed to the console or to your output location. You will have compiled in debug symbols though, so you'll still have a debug version of the library that's probably a little bit bigger in size. For post-quantum algorithms, we support ntrue currently, along with the quantum safe handshake extensions. They will be enabled in the benchmark, I believe, if you have ntrue enabled. That's disabled by default since it requires a third-party library to be linked against wolfSSL.
Alrighty. Hi, thanks for the demo. Thank you. Is it possible to include timestamp information in wolfSSL debug output, or is it just announcements of events?
So the default configuration of our log messages don't include the timestamp. We provide a way for you to register your own logging callback function. And so that would be one way that you could make that format whatever you would like. And that might be including timestamps in there as well.
Is there a command line version of wolfSSL, like an alternative to OpenSSL CMD?
Yeah, good question. So we call it wolfClue, the wolf command line utility. Right now, I would say, that's in alpha stage, and you can find it on GitHub if you look in our wolfSSL-examples repository. It does support, some of the basic operations, but given that it's still in alpha form, far from complete.
Awesome. Which ECC curves do you support? Is P256 compatible with TPM 2.0?
Sure. So we support a bunch of different ECC curves. Most of the common ones that people are using today, things like the NIST curves, the brain pool curves. We default to NIST, the P256 curve. I believe that is compatible with TPM 2.0. We could definitely double check on that and look into, Wolf TPM is another one of our products surrounding that topic.
Awesome. What is the VS/NTRU solution?
Yeah, good question. VS/Entru is a Visual Studio solution that's set up to compile wolfSSL with Entru support linked against the Entru library.
Cool. And then this person's wondering if your cart pitch would make a useful quick reference / getting started guide. Will you be making the charts available?
We'll be making the slides available. Charts, I guess. I'm not exactly sure what charts you're mentioning, but if it's in the slides, we'll for sure share them. And if on our website we have a lot more charts and graphs on benchmarking and such, which also would be helpful.
Awesome. Can you describe what wolfBoot does?
Yeah, so wolfBoot is a newer product for us in the last couple of years. It's a secure bootloader implementation designed, originally for microcontrollers, but we've made it a little broader currently. We support a bunch of different platforms. It operates on a kind of a two partition design where you have your current running firmware image, and then you have an update partition. And wolfboot will handle updating the firmware from the update partition to your main partition in a secure manner. And if it's not validated or authenticated correctly, it'll roll it back to the old version.
Great. Would configuring with debug slow the performance down?
Yes, in general, running with debug enabled is going to hamper your performance. That's correct.
What is the best way to use wolfSSL in an already existing embedded product? Can you, I guess, add source files and include paths to the makefile or compile wolfSSL somehow as library and link it?
Yeah, so I guess it will depend on what your embedded project looks like. You can cross-compile the library through the configure script, which would allow you to, have an embedded tool chain and cross-compile wolfSSL for your target, and then link that library into your existing application. We also have people who just, pull the wolfSSL files directly into your existing application and compile it. So there's a couple of routes to go depending on what you prefer.
Okay, how can we compile wolfSSL for VxWorks?
So for VxWorks, we have one defined called wolfSSL_VxWorks. And we do have some documentation around that I believe it's in the IDE directory. I want to say under the Workbench subdirectory. I'd have to double check, but you could also, just shoot our support team a quick email at support@wolfSSL.com, and they'll also be able to point you towards the right resources there.
Fantastic. Do you have an assembler implementation of P-521?
I believe we do. It depends on the platform support. We've written assembly for, x86, x86-64, and some of the ARM variants. So I would recommend that you maybe either take a look at some of our documentation around assembly, or reach out to our support team and they'll confirm if we've got yours in there or not.
Alrighty, and that was we have one more question. Is wolfTPM a simulator, and how does it integrate with the TPM 2.0 TS?
So wolfTPM isn't a simulator itself. So it would be interacting directly with a TPM 2.0 module from something like Infineon. And we essentially we've replaced kind of the shim that would be the vendor TPM library. So you would just use Wolf TPM directly in between the TPM module and your application, or the TPM module and something like wolfSSL.
Okay, thank you everyone for attending this webinar. As a reminder, this webinar is recorded and will be made available via our YouTube channel. And right before we leave, we have one last question. Can you please explain the toolchain parameters for the .configure line?
So I'm guessing the toolchain parameters are in reference to cross-compiling. And so configure will accept, several variables. Like, one, for example, would be CC, which would be your compiler. But there's also, if you follow kind of common cross-compiling instructions, there's a way for you can set host equals to your toolchain that you're using. And that will, as long as your toolchain is installed and available on your platform, cause configure to use the GCC and the LD and such from that toolchain.
Awesome. Okay, I would like to thank everyone for attending this webinar. I would like to again remind everyone this webinar is recorded and will be made available via our YouTube channel. We will also be making these slides available through email following this presentation. And as a reminder, I'd like to invite everyone to follow us on Twitter at wolfSSL, as well as all of our other social media. And if you have any additional questions about the webinar or any of our other products, please email us at facts@wolfSSL.com, and we would love to thank you, or we would love to help you. And thank you everyone for attending.